What is up, y'all? Welcome back to my channel. I hope that you're all doing well. It's been a few weeks since I uploaded my last video, and on my last video, I had someone ask me a question in the comments. Now, I told this person I would make a video giving a more in depth explanation or response. And the reason why I wanted to do that is because of the way that the question was worded. Sure, I could have, maybe answered somewhat simply, I guess you could say, but let me just read the question, and many of you will understand why I wanted to do this video. So the question is, why do things that weigh less fall at a slower rate? Maybe I'm just dumb, but when the ground moves upward, the weight of an object does not come into play at all. First off, you're not dumb. Asking questions is never dumb. In fact, I don't think there's enough people out here asking questions. I don't think there's enough people looking into it for themselves, to be totally honest with you, but asking questions is never dumb. So you're not dumb. Now, here's the issues that I had with the question. The first thing is, why do things that weigh less fall at a slower rate? Well, I'm not in this person's head. I don't know what they comprehend and what they don't, right? So, from my position, the object is not physically moving down. Okay? So, if they don't know that, if they don't know that that's my position and I just assume that they do, right? Then and I go on to try to explain, it's not going to make any sense to them because they think I'm explaining it from a position where the object is physically moving down when in my position it's not. So that's the first issue. You got to get your mind wrapped around the fact that the object is not physically moving down. It just looks that way to you. The second issue was, why do things that weigh less, so objects and their weight, matter and its weight? Well, how does weight work on an earth in constant motion? That is something that's important to understand if you're going to question, different scenarios where weight might or might not be involved. So, or be a factor. So, one mistake I see a lot of people making, especially flat earthers, is that they seem to think that they know these more in depth uh, uh, workings, if you will. So, like the mechanisms of motion and different things like that. It's like they assume that they already know these things, that the things they think they know are correct. And so they don't stop and think that, is it a possibility that I'm wrong about this? Have I went to verify that any of that's even correct before I start questioning this other stuff? So that's a big issue. I see it happening all the time. And so that's why I think it's important to break this question down a little bit and make sure that some of these other things are understood first. Otherwise, if I just start explaining it, again, people are going to be confused. They're not going to know what the hell I'm talking about. So here's the thing. In this video, what I've done is I've made several visual aids talking about weight, how we get the effect of weight on an earth in constant motion, why our weights on a scale are different, why we don't all have the same weight, inertia, what that is and how it comes into play, maybe a few other things in there. And then towards the end, I made a short visual aid to, in a nutshell, answer this person's question. So for those of you who already understand all of this, if you want to skip the video, I totally understand. I don't blame you. But for everybody else, I hope that maybe you'll come to a better understanding, if nothing else, at least a better understanding of what I claim and what I don't, so that there's no misrepresentation or confusion about where I stand. Okay? So we're going to take a look at these clips that I've put together for you. I hope that you all enjoy it. Let's get into it. All right, so for the first part of the question, why does an object that weighs less fall at a slower rate? This is a visual aid just to explain what's actually happening when we let an object go. So what's actually happening here is you have the ground, okay? It's moving upward. We'll just say 100 miles an hour, and it's moving at a constant speed. I am standing here, and I am holding an object in my hand. Okay, that means that me, the ground, and the object, well, you get the drift, are all moving upward at the same speed together of 100 miles an hour. Okay, we're all moving together when I'm holding that object in my hand. All right, so that's first. Now, when I let this object go, all right, now I've let the object go here. Let's fix that. I've let the object go. What's happening to it? The object doesn't immediately just start moving down. It doesn't stop in midair. It doesn't do any of those things. Okay. The object continues moving up just like it was when I was holding it, but it starts to lose its speed. Okay. So it's going to start every second that goes by. It's lost a little bit of its speed. So it starts 99, 98, 97, 96, 95. It starts to lose its momentum. The speed, the momentum that the earth was giving it when I was holding it. Okay? So that's what's actually going on. The object is not actually falling. It only appears to be falling because you are standing on the earth moving upward at a constant speed. So, to your perception, since that object is now slowing down, moving slower upward than you are, it gives you the optical illusion that the object is moving down when it isn't really moving down at all. All right, for this next visual aid, we're going to talk about weight on an earth in constant motion. What is it that causes weight? Well, for weight, you need two things, okay? You need the Earth's motion, that force, and then you also need something else, something called inertia or resistance to motion, okay? Now, what I'm going to do is I'm going to write this up top so that we have it, so we can look at it as we go through this, right? So you need inertia, which is resistance. All right. Then you need motion or force. All right. And then you get the effect of weight. Yes, weight is an effect. It is not a force. Some people think that weight is a force. It is not. Weight is also not a property of matter. It is an effect. It is the effect of inertia and motion. Those two things together are needed for the effect of weight. So let's start by talking about how we get weight on a scale on an earth in constant motion. It's very simple, really. You have the ground. The ground is moving up, we'll just say at a constant speed of 100 miles an hour for simplicity. And let's say I have a scale here, okay? Now, I am going to stand on this scale, all right? Let's talk about what's going on here. Okay, so what's happening here is you have the earth pushing up on this scale, right? And then you also have the scale, which is being pushed up on my feet here, okay? Now, so what you have is this upward motion like this. So the ground, the scale, and me are all moving up at that constant speed, okay? Now, at the same time, we have inertia, which is resistance. What is inertia? Well, imagine inertia as being sort of like a medium, Okay, so what I'm going to do is I'm going to do this, because this is sort of how I would explain inertia. I want you to imagine that you're at the bottom of the ocean, okay? And any direction that you move, because you're surrounded by water, you're going to experience a resistance on you from that water. If you try to throw something under the water, say a ball, right, that ball is also going to be affected by the water, creating a resistance on that ball. So that ball is going to slow down and lose its speed due to the resistance from that water. Well, inertia works similarly in nature, right? It's sort of like a medium that's all around us. It's always there, okay? And the thing is I can't go outside and point it out and say, look, there's inertia. You can see it. It doesn't really work that way. It's a lot like air, right? We know that it's there. It's all around us, and we can see the effects of it on matter. We can see that much, right? We know that it's there because of that, but I can't point it out to you. I can't point at it and say, there it is. So, as I said, right, we have the upward, let me fix this, make sure you can see it okay. We have the upward motion like this, right? So there's our motion, our force pushing us upward. And then we also have the opposite resistance of inertia, which is going to work in the opposite direction. There's your inertia. So in this case, we have the effect of motion. So that means that there's going to be a pressure on the scale. If this is me, it's going to read around 120 pounds. Now, you might be wondering, like, why is it that we have different weights? Why is it that not everybody's weight is the same? Well, the reason for that is differences in mass. So, something with less mass will experience less resistance, where something with more mass is going to have experience a greater resistance. So think of like a feather and a bowling ball, right? A feather has much less mass, so its resistance is going to be a lot less than a bowling ball will be. That's why if my reading on the scale say is 120, right? But then let's say a man were to stand on a scale beside me and he has more body mass than I do, the resistance that he experiences on his body is going to be greater, which means that the pressure on the scale for him is going to be greater as well. So he's going to have a higher weight. So again, you need these two things to have weight. That's how that works. Now, the next question is, what about an object when we let it go in free fall? How does that work? Well, I'm going to show you that in the next visual aid. All right, so now let's talk about an object in free fall. Okay, here's the thing, right? If we have the ground and the ground is moving at an upward trajectory like this, we'll just say again at 100 miles an hour, try to be consistent here, right? And I let go of an object. You need to, in this scenario, consider the fact that we're in the medium of air. All right. And the object that I let go, right, is more dense than the air. So let's talk about what we actually have in this scenario and what we don't when it comes to inertia, motion. We need to make sure we have both of these things acting on that object to have weight. If we don't have those things, well, then we don't have weight. So let's take a look at what's going on here. So what's happening in this scenario is this, right? You have inertia. Remember, it's always there. So we've got that acting this way on the object. So that's taken care of. But now we need to make sure that we have the force motion, right? acting on the object as well. Now, remember, as I said, just to remind you that the object is not physically moving down. Okay, keep in mind that object is still moving upward, losing its speed, the speed that it had when I was holding it. Okay, so it's still moving upwards. Now, the earth is moving up like this. Let me get a different color here so I feel like you can see it a little bit better. The earth is moving up like this, okay, pressing on the air. The air is pushing up here on the bottom of the object. But remember, the air is not dense enough to continue pushing that object upward like this. Most of the air is just going to kind of move over the object like this. Some will push on the bottom of it, but it's not dense enough to provide enough support here to actually push the object up. So in this scenario, you don't have the force motion up this way and through that object, pushing that object upwards like this. Okay, so in this scenario, the only thing you have is resistance. You don't have the motion force, which means that the object in this scenario is weightless. Because you need both, remember? You need resistance and that motion force. Now, to make this just a little bit clearer, maybe just to help make a little more sense out of it, let's just change the medium real quick, okay? Let's say the object is in a super dense oil instead, all right? Now, you have the resistance, remember, it's always there, so that's going to be acting on the object automatically. It's always there, all right? But the earth is pressing up, just like it does on the air. It's pressing on this oil, pushing up. But now the oil is so much more dense than the air was that it can actually push this object upwards more than the air could. Okay? It might not be pushing it enough to push it at a constant speed of 100 with the earth, but it's pushing it more than the air. It's actually able to push it up more. So in this scenario, you do have the motion force, which means you do have weight. Now, if we could put that object on a scale in that oil and weigh it, it's not going to weigh as much as it would if it were sitting on a scale on the ground, right? Its weight is going to be less because you don't have that full pressure on the scale like you would in the air, in the medium of the air, it's just sitting on the ground. So I hope that that kind of helps to clarify. You know, if we were able to, I don't know, change this medium again to something um, nearly as dense as the Earth, well, then this object is going to be moving up at nearly being pushed up by the medium in the Earth at nearly the constant speed of the Earth. So in that case, you're going to have more weight, right? Because that pressure is going to increase. So I hope that that made it a little bit more clear in terms of the difference in quote unquote free fall. And then, like in this scenario with the oil, the object isn't considered to be in free fall. And in this scenario with the oil, it does have a weight. It's weightless in the air, not in the oil. So, anyways, I hope that that clarifies that a little bit more when it comes to releasing objects into different mediums as far as weight goes. I wanted to include this clip as it is a real world example of what I explained in the visual aid clip we just watched. I talked about how the earth pushes up on the medium and the medium pushes up on the object. If the medium isn't dense enough to push the object, then the medium will just move up over it until the ground reaches the object. To you, it will look like the object is moving down. If the medium is dense enough, it will physically push the object upwards. This creates the buoyant effect. In this clip, you will see that when the object is pressed hard to the bottom of the container, the water is forced out from under it and the object will sit on the bottom of the container. Since the object isn't sealed tight to the bottom, the water, being a liquid, will slowly make its way underneath the object again. Once there is enough of the medium under it, the object becomes buoyant again and moves upward. Take note that the medium needs to be underneath the object and moving in an upward motion to push the object up. Now, knowing that inanimate matter doesn't move without a force and the medium is inanimate, just like the object is, what do you think is moving the medium? The force of the earth is moving up, pushing the floor up. The floor is pushing the table up. The table is pushing the container up. The container is moving the medium up, and the medium is moving the object up. Without the primary force of the earth moving in the first instance, nothing in this clip would be in motion. I'm just going to let this clip finish playing out so that you can see once again what happens when the medium is under the object. All right, now for the main question, why does an object with less weight fall at a slower rate? Here's the thing, it all comes down to your perception. Okay, we already talked about how objects are not falling, they're still moving upward. We talked about weight and how that's caused. We've talked about inertia. So we've talked about a lot of things. Let's say this is the ground, okay? This is the ground. It's moving upward at 100 miles an hour. Let's say you've got two buildings here, okay? You've got a person standing on this building and one standing on this building, and each of them are going to drop an object, okay? One is going to drop a feather, the other is going to drop a bowling ball, and you are standing down here watching these objects, quote unquote, fall. All right. Now, remember, neither of these objects are actually moving down. They're still both moving upward, but they are losing their speed. The feather has less mass than the bowling ball, which means that its resistance to motion is going to be less than the bowling ball. This means that the feather is going to lose its speed much slower than the bowling ball will. So the bowling ball is going to slow down much faster than that feather is. What that means is that the ground, still moving at this constant speed, is going to come up and smack the bottom of that bowling ball much quicker than it's going to reach the feather. Now, to your perception, standing on the ground looking at these two objects, it's going to look to you as if they're falling down, first of all, when they're not. But second of all, remember, you're standing on the earth moving at 100 miles an hour still. So you are going to see the feather as moving to the ground much slower and the bowling ball much faster. So again, it's just an optical illusion, right? It's just how you perceive it because you're standing on the earth in constant motion. So I hope that that kind of clarifies that a little bit. The feather doesn't lose its speed as quickly as the bowling ball. So say the feather only drops down to 90 miles an hour. where the bowling ball drops down to 10. If you look at those numbers in comparison to the Earth's 100 miles an hour, it's not too hard to figure out that the ground moving 90 miles an hour faster than that bowling ball is going to come up and hit it pretty damn quick, where it's going to take more time for it to reach the feather because the feather is moving almost as quickly as the Earth is. Because the feather's going 90 miles an hour and the ground's moving at 100. There's only a 10-mile-an-hour difference. This is going to change the way that you perceive it. Because again, to you, it's falling down when it isn't. It's still moving up, just slowing down. And one is losing its speed faster than the other. So I hope that that clarifies. I hope that all of these visual aids help to clarify the question. All right, guys, there you have it. That's the video. For the person that left me that question, I hope that some of this was able to clarify for you some of these different aspects in terms of my position and what I claim and what I don't. I hope that, some of it was able to give you more insight into the question that you're asking. I understand that my position can be hard to comprehend, but it's really not that complex. It's actually quite simple to grasp once you understand things at a more fundamental level. Once you understand how these things work, I keep saying it because I don't know another word to use, but like at a deeper level, right? So understanding motion and how that works, right? Understanding that inanimate matter can't move by itself. You need something, you need a force to put something in motion, right? So you need something that's already in motion to contact something else and put it in motion. It's like a chain reaction. That's basically what we're seeing in reality. A lot of chain reactions between the earth and the medium. And then the objects and matter within those mediums being affected by that motion. So, anyways, that's it. If you have any other questions, feel free to leave them. I'll do my best to answer them as quickly as I can. Just please be patient with me. Sometimes it's kind of hard to find time to put these together. So I hope that you can all understand that. Until next time, I'll catch you guys later. See ya.